right, one common application of exponential equations is radioactive decay. All right, and so the concept of radioactive decay is after a certain amount of time, the amount of material is now half. Okay, so all right, so pretty much what happens is we start with an amount, okay, and then after a certain amount of time, that value decreases by half, right? And then after that same amount of time, it decreases by half again, right? Okay, so now we're doing repeated multiplication. Okay, so pretty much you could write this as we take your amount and we multiply it by a base to an exponent. Okay, and then we'll just write that as h. So h is the amount of half-lives. Okay, so each half-life that happens, the value decreases, or you take half of it, the current value, right? So what's the initial mass when t equals 0? What we would do is we take this equation and we'd plug in 0. Well, 0 over 29 is 0. Anything to the 0 power is 1, which means that we're going to have 10 grams at the start. All right, so if I look at this model, this stands for initial amount, okay, and that number in this case was 10. Right? So how much of the initial mass is present after 80 years? Okay, we would plug it into the equation. So y would equal 10 times 1/2 to the 80 over 29. Okay, I'm going to work this problem out like I would if the calculator didn't have orders operations. Okay, so most of you will be able to just plug it in as it is. You might need to put some parentheses here, okay, so the calculator doesn't mess that up. Okay, but most of you will be able to just type this in. So again, I'm going to work it out like I would if I had to do all the orders operations. Okay, so we're going to figure out what that exponent is first. 80 over 29 is 2.7586, and it keeps going. In the middle of the problem, I'm going to keep quite a few decimals. At the end, I'm going to go to the nearest hundredth. Okay, so now I have to do the exponents. So if I do half, okay, that's 0.5. I'm going to take that to the 2.75862 power. So now I have y equals 10 times 0.147765. Okay, we're going to multiply that by 10, and it looks like I have 1.48 grams. All right, this number, it's exponential decay. It should be less than the start. Notice we are less than 10, so that's good. All right, if you think about how many times 80 goes into 29, 80 divided by 29 was 2. So it was 2 and a bit. So 2 half-lives, it would move down to 5 and then 2.5, and then we're a little less than 2.5. So this number seems to make sense. Okay, and then let's try one homework problem. So, all right, so we're supposed to complete the table to determine the balance A for this amount invested at a rate R and T and compounded N times per year. Okay. All right, so if I set my problem up, okay, my amount's going to be the principal times 1 plus the rate. Okay, we're doing 68, so my rate would be 0.03 over n. Okay, the amount of times compounded. Okay, that's what's changing. So, so I'm just going to set my formula up here. So that n times, and then t is always 40. Okay. All right. So the first part of the table, we're going to let n be 1. Okay, so we would type it in as n equals 1. Okay, so 25. So if we want to show the work for that, so when, let's say n equals 1, here's the work. I'll have to edit the bell out. 1 plus 0.03 over 1, so the 1 times 40. So that's going to look just like regular exponential growth. You'll get your answer, and you'll put it right here. Okay. Then when n equals 2, you're going to do 2,500 times 1 plus 0.03 over 2 to the 2 times 40, and then you plug that answer there. Okay. So that's how you would do that.